So the rate of radioactive decay, the rate of change in the amount of radioactivity is consistent and different for each isotope. It can be measured with a Geiger counter. And so each radionucleotide has a particular length of time required to lose half of its radioactivity, which means it has a consistent half-life. And if you remember back to chapter 13 when we talked about rates and kinetics and half-lives, the process with a constant half-life follows first-order kinetics. So radioactive decay follows first-order kinetics, but it's also not affected by temperature, so it's not a chemical reaction. So the kinetics of radioactive decay, the rate is K, the rate constant, times N, the number of radioactive nuclei. And the half-life for every radioactive nuclide is 0.693, which comes from the natural log, divided by K, that rate constant. The shorter your half-life, the more nuclei will decay every second. And in the chemical slang, we say that it's hotter. A hot sample decays faster. So here are some half-lives of various nucleides. Carbon-14, used to date things, has a half-life of 5,730 years. You can see some half-lives are really long. Thorium-232 has a very long half-life. Thorium-219 has a very short half-life. Just depends on what the nuclide is. And we know that half the radioactive atoms will decay every half-life. So after one half-life, you have 50% of your original sample. After two half-lives, you have 25%, three half-lives, 12.5%, etc., etc. So let's work through an example. This is not set up right. So if you have a 1.35 milligram sample of plutonium-236, calculate the mass that will remain after 5 years. So we have our mass. You can look up the half-life. So the half-life is 2.86 years. We know that our half-life is 0.693 divided by K. And we know from rate laws that the natural log of your amount at that time divided by your starting amount is the opposite of KT. So we can solve for our K, which is what these pink numbers are doing. So our half-life is 0.693 divided by K. We know our half-life is 2.86 years. So if you take 0.693 divided by 2.86, we get a K value of 0.2423 per year. Let me erase my marks there. And then we can plug that in over here. We know that we want to know our amount at our time. If we take both of these to the power of E, we can solve for, so N0 e to the minus KT is going to be our amount at that time. So if you plug in those numbers, we can get a amount at that time of 0.402 milligrams. So let's work this through on a page that does not have overlapping text. Radon-222 is a gas that is suspected of causing lung cancer as it leaks into houses. It's produced by uranium decay, assuming no loss or gain from leakage. If there's 10.24 grams of radon-222 in the house today, how much will there be in 5.4 weeks? And our half-life is 3.8 days. So our N0 is 10.24 grams. Our half-life is 3.8 days. We know that our half-life is 0.693 over K. So we can solve for our K value, And then we also know that other equation, let me write down, the natural log of NT over N0 is equal to negative KT. Okay, so we can solve for our K value. So 3.8 days is equal to 0.693 over K. So our K value is 1.82 times 10 to the minus first per day. So then we know our natural log of NT, which is what we're looking for, over our initial amount, 10.24 grams, is equal to negative I'm not just going to write 0.182 times our time, 5.4 weeks. 5.4 weeks times 7 days in 1 week gets me 37.8 days. The units just have to be consistent. It doesn't really matter what you use. You could also convert your half-life into weeks if you wanted to. So our NT is going to be e to the negative 0.182 times 37.8 times 10.24. So our amount at the time is 0.0105 grams. So that makes some sense because we've gone through basically 10 half-lives, so we don't have a lot left. And I erased the relevant part here, but that's the correct answer. Anyway, radiocarbon dating can be used to determine an object's age. You've probably heard of this. We can date artifacts using the amount of carbon-14 left. Here's a table showing the percentage of carbon-14 compared to a living organism versus the object's age. While things are living, the carbon-14 to carbon-12 ratio is consistent because the organism is going to replenish its supply of carbon. But once the organism dies, your carbon-14 is going to slowly decay into nitrogen. The limit is going to be about 50,000 years old. And after that point, the radioactivity from carbon-14 is below background radiation. So let's work through an example here. An ancient skull gives 4.50. This is just basically units of radiation. If a living organism gives 15.3, how old is the skull? We're going to solve this the same way we did those other ones. We know that our rate is 4.50. Our rate of radioactive that, and our rate at our initial rate is 15.3. We know our half-life is 0.693 divided by K. And you'll be given all of those equations. And our half-life for carbon-14, you also need to know which again would be given to you in a question, is 5,730 years. Just looked that up from a couple slides ago. So we can find our K value. So our K, if we plug in those numbers, works out to be 1.209 times 10 to the minus fourth. Per year. So then we can plug in, based on this equation, the natural log of our rate of detection at a specific time divided by the rate at time 0 is equal to negative KT. So the natural log of our 4.50 divided by 15.3 is equal to negative 1.209 times 10 to the minus fourth times our t. We can rearrange and solve that, and we get a t value of 1.0 times 10 to the fourth years. All right, next question. Archaeologists have dated a civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon for a rice grain found at that site? I'm going to just use my K value that I calculated on the last slide. So my K value for carbon 13 is 1.209 times 10 to the minus fourth per year. And I know that my natural log of my rate at my time over my rate initially is equal to minus KT. That's from the integrated rate law. So if I take, so natural log of, this is what I'm looking for, divided by 20 is equal to negative 1.209 times 10 to the minus fourth times my time is 15,600. So I can rearrange that and solve for my rate at my time by taking my right side here to the power of e and then multiplying by 20. Then I get a rate equal to 3.03, and then my units are counts per minute grams Celsius. So there we go.